Take a deep breath. In that single, simple act, you have inhaled nitrogen from an ancient atmosphere, oxygen forged in the heart of a long-dead star, and argon that has likely remained unchanged since the Earth first formed. Every atom within you, every particle that constitutes your consciousness, has a story that stretches back billions of years. To understand these stories is to understand the universe itself. Our journey begins not in the distant cosmos, but right here, with a single atom of carbon inside your own body. This carbon atom, the versatile backbone of all known life, was not created in the Big Bang, the initial cosmic explosion, an event of unimaginable energy and density, was too hot and too brief to forge anything heavier than hydrogen, helium, and trace amounts of lithium. For the first few 100 million years, the universe was a vast, dark expanse of these simple gases, slowly coalescing under the gentle but relentless pull of gravity. So where did this atom of carbon, the very stuff of you, come from? Its birthplace was a furnace of unimaginable power, the core of a star at least 5 times more massive than our own sun. Inside this stellar giant, gravity squeezed hydrogen atoms together with such force that they fused into helium, releasing a torrent of energy that pushed back against gravity's collapse. This is the process that powers stars, a delicate cosmic balancing act. For millions of years, this star burned a stable beacon in the primordial darkness, but eventually, the hydrogen in its core ran out. Gravity, the patient victor, began to win. The core contracted and heated up to temperatures exceeding 100 million degrees. At this point, a new miracle of physics occurred. Helium atoms, previously inert, were slammed together with such violence that they fused into beryllium, which then instantly captured another helium atom to become carbon-12. Your carbon atom was born. This process, called the triple alpha process, is astonishingly delicate. Its existence was famously predicted in the 1950s by the British astronomer Fred Hoyle. He calculated that for carbon to be as abundant as it is, there had to be a very specific, undiscovered energy state in the carbon nucleus, a resonance that would make the reaction far more likely. He stormed into his colleague William Fowler's lab at Caltech, demanding they look for it. They did, they found it, and Fowler would later win a Nobel Prize for his work on stellar nucleosynthesis. Hoyle, the man who predicted the very mechanism of our existence, was controversially overlooked. His insight, however, remains one of the greatest triumphs of theoretical astrophysics. You exist because of a finely tuned quantum resonance inside a star. But the story of your carbon atom doesn't end there. For it to become part of you, it had to escape its stellar prison. The star continued its life, fusing heavier and heavier elements in concentric shells around its core, like a cosmic onion: carbon, then neon, oxygen, silicon, and finally iron. Iron is the ultimate stellar ash. Fusing iron atoms does not release energy. It consumes it, with no energy pushing outwards. Gravity won its final, catastrophic victory. In less than a second, the star's core collapsed. The outer layers, containing your newly forged carbon atom, came crashing down and then rebounded off the incompressible core in a titanic explosion, a supernova. For a few brilliant weeks, this single exploding star outshone its entire galaxy, spewing its precious cargo of heavy elements across interstellar space. Your carbon atom, along with gold, silver, oxygen, and silicon, traveled for eons through the void, a ghost of a dead star. Eventually it drifted into a new swirling cloud of gas and dust, a nebula. This nebula, seeded with the remains of previous stellar generations, was the crucible for our own solar system. Gravity once again worked its magic, pulling the material into a spinning disk with a dense, hot center. This center ignited to become our sun. Farther out in the disk, dust and gas clumped together, forming planetesimals, then protoplanets, and finally, the planet we call Earth. Your carbon atom was there, baked into the very rock and gas of our nascent world. Over billions of years of geological activity, volcanism, and the eventual rise of life, That single atom was cycled through rock, air, water, and eventually into a plant eaten by an animal, and ultimately into the food that built the very cells that are reading these words. You are, quite literally, stardust. But is our star our sun alone? For millennia, we looked up at the Milky Way, that faint, shimmering band across the night sky, and saw it as a celestial river or a cloud. It took a telescope in the hands of Galileo Galilei in 1610 to resolve it into what it truly is, an unfathomable number of individual, distant stars. We were living inside a vast, disc-shaped city of stars. For centuries after, we believed this city was the entire universe. It was a comfortable, if grand notion. This view was shattered in the early 20th century. At the Mount Wilson Observatory in California, a great debate raged. Astronomer Harlow Shapley argued that the spiral nebulae, faint, fuzzy patches seen through telescopes, were small gas clouds within our own Milky Way galaxy. Heber Curtis, on the other hand, contended they were island universes, entire galaxies just like our own, but at immense distances. The debate was settled in 1923 by a quiet, meticulous astronomer named Edwin Hubble. Using the new 100-inch Hooker telescope, the most powerful in the world, he was able to resolve individual stars within the Andromeda Nebula. One of these was a Cepheid variable, a special type of star whose brightness pulses at a rate directly related to its true luminosity. By comparing its apparent brightness to its true brightness, Hubble could calculate its distance. The number he came up with was staggering, nearly 1 million light-years. Andromeda was not a cloud in our backyard. It was a sister city of stars, a galaxy in its own right, and it was incomprehensibly far away. The known universe had just expanded 100,000-fold in a single observation. Our Milky Way was just one of billions of galaxies. Hubble, however, was not finished rewriting our understanding of reality. As he measured the distances to more and more galaxies, he also analyzed their light. He noticed something peculiar. The light from nearly every galaxy was stretched, or redshifted, as if it were moving away from us. More remarkably, the farther away a galaxy was, the faster it appeared to be receding. The conclusion was inescapable and universe-altering. The universe itself is expanding. It's not that galaxies are flying through a static, empty space. The very fabric of space-time is stretching, carrying the galaxies along with it, like raisins in a baking loaf of bread. This discovery was the first piece of physical evidence for what would become known as the Big Bang Theory. The idea had been proposed a few years earlier, in 1927, by a Belgian priest and physicist named Georges Lemaitre. He had solved Einstein's equations of general relativity and realized they implied a dynamic, evolving universe. If the universe is expanding now, he reasoned, then in the past, it must have been smaller, denser, and hotter. Tracing this back far enough, you reach a point of infinite density, a primeval atom from which space and time itself erupted. The scientific establishment, including Einstein, initially dismissed the idea. Fred Hoyle, the same astronomer who predicted our carbon origins, mockingly coined the term Big Bang on a BBC radio show to ridicule the theory. The name, ironically, stuck. But if there was a Big Bang, a moment of intense heat and light, there should be some remnant, some afterglow of that creation event. In the 1940s, physicists George Gamow, Ralph Alpher, and Robert Herman calculated that this residual heat should still permeate the entire universe, cooled by billions of years of expansion to a faint microwave glow, just a few degrees above absolute zero. Their prediction was ignored and forgotten. Then, in 1964, at Bell Labs in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a large horn antenna for satellite communication. They were plagued by a persistent, faint background hiss, a noise that came from every direction in the sky, day and night. No matter where they pointed the antenna, they checked their equipment, rewired connections, and even cleaned out what they described as a white dielectric material, otherwise known as pigeon droppings, from the horn. The hiss remained. It was a uniform, unavoidable noise floor. Frustrated, they happened to learn of the work by physicists at nearby Princeton University, who were building a detector to search for the very cosmic afterglow predicted years before. Penzias and Wilson had stumbled upon it by accident. They had found the echo of creation. This discovery, the cosmic microwave background radiation, was the smoking gun for the Big Bang. When we map it across the entire sky as satellites like COBE, WMAP, and Planck have done with increasing precision, we see a baby picture of the universe taken when it was only 380,000 years old. It is an almost perfectly uniform glow, but within it are minuscule temperature fluctuations, variations of only 1 part in 100,000. These tiny ripples, these slightly denser and slightly less dense patches in the primordial soup, were the seeds. Under the relentless pull of gravity over billions of years, the denser regions grew, pulling in more and more matter, eventually forming the vast cosmic web of galaxy clusters, filaments, and voids that we see today. Every star, every galaxy, every structure in the universe can trace its origin back to these faint quantum fluctuations in the seconds after the Big Bang. This picture of the universe, from Big Bang to cosmic web, felt remarkably complete. But as our observations improved, new mysteries emerged. In the 1970s, astronomer Vera Rubin was studying the rotation of galaxies. She expected to see stars on the outer edges moving more slowly than stars near the center, just as the outer planets in our solar system orbit more slowly than the inner ones. Instead, she found that the stars on the periphery were moving just as fast as those closer in. They were moving so fast, in fact, that the visible matter in the galaxy, the stars, gas, and dust, could not provide enough gravitational pull to hold them in orbit. The galaxies should have flown apart. There had to be something else there, something massive and invisible, providing the extra gravity. She had found the first strong evidence for dark matter. Today, we know that the stuff we are made of, the atoms forged in stars, the normal matter, makes up only about 5% of the total mass and energy content of the universe. About 27% is this mysterious dark matter. It doesn't emit light, absorb light, or interact with our matter in any way except through gravity. It forms a vast, invisible scaffolding, a ghostly halo around galaxies within which our visible world is embedded. We don't know what it is. It could be a new type of subatomic particle, something predicted by exotic physics theories, but not yet detected in our earthbound laboratories. It is a profound cosmic humility check. We are not even the main form of matter in the universe. The final shock came in 1998. Two independent teams of astronomers were using distant supernovae as standard candles, much like Hubble used Cepheid variables, to measure the expansion rate of the universe more precisely. They expected to find that the expansion was slowing down, pulled back by the gravity of all the matter within it. Instead, they found the exact opposite. The expansion of the universe is accelerating. It is speeding up. To explain this, physicists had to invoke something even more bizarre than dark matter, repulsive force, an anti-gravity property of space itself, which they named dark energy. This strange energy makes up the remaining 68% of the universe. It is the dominant component, and its influence is growing. This discovery paints a startling, and perhaps lonely, picture of the deep future. As space continues to expand at an ever-increasing rate, galaxies will be pushed away from us faster and faster. Eventually, they will recede from us at speeds greater than the speed of light. Their light will never reach us again. One by one, the galaxies will disappear from our view. 1 trillion years from now, our local group of galaxies will have merged into one supergalaxy, but the sky beyond it will be black and empty. The universe will become an impossibly vast and lonely place. The stars within our own galaxy will eventually burn out. The red dwarfs, the longest-lived stars, will finally exhaust their fuel after trillions of years, fading into cold, black dwarfs. The universe will enter a degenerate era populated only by the dead remnants of stars, black dwarfs, neutron stars, and black holes. Even these are not eternal. Over timescales that beggar imagination, protons themselves may decay, causing all matter to dissolve into a thin soup of radiation and particles. The black holes, the last bastions of organized matter, will slowly evaporate through a process known as Hawking radiation, leaking their mass energy back into the void over googles of years. Eventually, after a span of time so long that the age of the universe so far is an insignificant rounding error, the last black hole will evaporate in a final, weak flash of light. The universe will reach a state of maximum entropy, a near-perfect vacuum filled with a homogeneous, low-energy sea of photons and elementary particles. It will be cold, dark, and empty, a state known as the heat death of the universe. Time itself may lose its meaning, and what of your carbon atom after its long journey? From the Big Bang's simple gas to a star's fiery heart, from a supernova's blast to the formation of a planet after its brief, improbable participation in a conscious being capable of contemplating its own origins, it will be unbound. It will drift alone in the final, cold, dark emptiness, its grand story seemingly at an end. But perhaps this is the wrong way to see it. The wonder is not in the final state, but in the journey, the incredible, connected chain of events, guided by the fundamental laws of physics that turn primordial energy into a star into an element into a planet, and a planet into a mind. The universe, for a brief flicker of cosmic time, created a part of itself that could look back and understand the whole. All the wonders of the universe, from the quantum dance inside a star to the accelerating expansion of space, from the echo of creation to the prediction of its end, are not just things that happened. They are the story of how you came to be. And you are here now, a temporary collection of stardust, with the privilege of knowing it.